Hi, this is Mike Keenan here. Today I'm going to be going over static, dynamic, and connected routes. This is the configuration that we're going to use for router 1, 2, 3, and 4. A connected route is directly connected to an interface. So that's when you have an interface, say 10.1.1.0, or let's say the interface is 10.1.1.1, and he is in a /24 subnet mask. That means that he is directly connected to 10.1.1.0/24. Static routing is whenever we log into the router, we do a IP route command. We say IP route 10.1.1.1 255.255.255.255 to 10.2.2.1, and that's saying send to that next hop router. Dynamic routing is whenever we're using a protocol like OSPF or EIGRP to dynamically distribute routes from one router to another without having to log into every single router and do it manually. So that's what the difference is between those three types of routing. An important thing to remember is that the certain routes will trump other routes with what is known as a metric. So connected routes are always going to be number one. Static routes will be number two. And dynamic routes will be number three. So that's the order of importance. So connected routes will always trump static routes, and static routes will always trump dynamic routes. Okay, so starting off on the workstation down here in the green subnet, what we're going to do is attempt to ping the web server up here. So we're going to try to go from here to the web server and see what happens. Right now we don't have any routes configured. So we'll ping 10.5.5.15 and nothing. The reason for that is because those packets don't know how to get to the web server yet, but we're going to fix that here in a second. We're going to start off by configuring dynamic routing using OSPF. We're going to start off on router 1. We're going to say router OSPF 1. We're going to give him a router ID of 1.1.1.1, and that's kind of a serial number. You can kind of think of it as that is something that's going to be unique to the area, and that's going to be another term we're going to get to. The area that these routers are in. So we're going to say that basically his name is 1.1.1.1 for OSPF, and we're going to say which networks to advertise. So we're going to say network 10.1.1.0, 0.0.0.255. It's important to remember that those are wildcard masks. That's what you have to use with OSPF. And we're going to say advertise that in area 0. And we're going to do the same thing for 10.2.2.0. Area 0. So what that does, whenever we use this command here, router OSPF1, we're saying turn on OSPF and use 1 as the process ID. Now, the process ID isn't that important. It could be the same or it could be different on each router. And obviously, you want to make sure that you're advertising the right networks. So what happens is when we type in network 10.1.1.0, this command here, what we say is whatever interface is in that subnet, which you'll see over here, router 1 has an interface 10.1.1.1 in that subnet. So he's going to start sending out what's called link state advertisements out that interface to see if he can find any neighbors. And what we could do if we didn't want to, because there's no reason to send LSAs out that interface, so we could use a passive interface command. Over here, 10.2.2.1, you'll see it's in that subnet there in that command. So he'll start sending out LSAs out of that interface. And that's something that we want, because we want him to be able to form a neighborship adjacency to router 2 and to router 3. What that also does is it advertises those networks, and it tells every other router within area 0 that it has an adjacency with, or a neighborship with, that he knows how to get to these two networks. So we're going to go over here to router 2, and we're going to configure OSPF on him as well. We're going to say router OSPF 1, so that's turning OSPF on the router. We're going to say router ID 2.2.2.2. We're going to say advertise 10.2.2.0. We're going to say area 0. And when we do this, he's going to form a neighborship adjacency with router 1. See, there he is right there. He's located out of his gigabit Ethernet 0/0 interface. We're also going to do the same thing for 10.3.3. And we're done there. Let's go to router 3. Do the same thing over here. His router ID is going to be 3.3.3.3. He knows how to get to the 10.2.2.0 network. And he also knows how to get to the 10.4.4.0 network. And there he goes. He just formed an adjacency with router 1 and with router 2. And then last but not least, router 4. Turn it on. Router ID of 4.4.4.4. He knows how to get to the 10.3.3.0 network. And the 10.4.4 network. And the 10.5.5 network. And that's one that I didn't include on my command sheet here, so let me put that in there. There it is right there. So now if we were to look at the workstation, you can see that he's starting to be able to ping the web server because now he knows how to get there through the network. So what I'm going to do now is put a capture here. I'm going to put another capture down here. Now again, this capture here is up here between router 2 and switch 3. And you can see the pings taking that route as opposed to this route. And the reason for that is because down here it's a much slower speed, whereas up here it is a much faster speed. So the routers are able to talk to each other and negotiate which route is the fastest, and it's going to pick the one that's the fastest. But if we were to suspend this link, you see the ping stop, and you'll see him pop up over here in a second. What's happening now is the routers have to reconverge, and it usually takes around 20 to 30 seconds, at least for this small topology. That's how long it takes for it to reconverge. There it goes. Sending out the LSAs. There it goes. Now you see it starting to ping over here. So what's happened is previously it was going this way. But because we shut that link off, it reconverged and took the alternate path going this way and back. So that's the example of dynamic routing using OSPF. But what happens if we were to take this, turn the link back on? The packets will start to go the way that they're supposed to go, the faster route after it reconverges. But say that we added a static route. What do you think would happen? Well, let's see. If we came here to router 1 and we said we want to route for that host address, this is a subnet mask now. We're saying for this 32-bit address, 10.5.5.15, we're telling it go to 10.2.2.3. So we're telling router 1, if it's for that address, send it here to router 3. So we'll go to router 3. Well, let's hit enter and tell it that. Now let's see, workstation 1. So it's still going that direction. The reason for that is because we have not yet added routes for the round trip. You'll see that here. It's still going from router 2 to switch 3. So let's go to router 3 and add static routes here as well. Now we need to add static routes both directions. Oops, wrong one. I'm going to go to router 3. And let's go to router 4 and tell him how to get back. And now let's look and see. So you see the pings have ceased going that direction, and they are now going from router 3 to switch 4, taking the alternate path. The reason for that is because we've added static routes going both directions. So that's an example of static routes having a higher order of precedence over dynamic routes. And lastly, the thing to remember about connected routes is that no matter what, if there's an interface in that network, it will always take that interface to get to whatever host it needs to get to. So that's it for static, connected, and dynamic routes. I'll see you in the next video.